Okay. So my other classes are very behind, so I'm hoping if I record this, I might be able to catch them up. Morning. Yes, it is still before noon, so it's morning. All right, so when last we left off, we were looking at this question. I think we had finished it. So we wanted to find the reference angle and then use that to find the coordinates for 7 pi over 6. So I'm just going to run through it real quick. The reference angle, remember, is the angle between the terminal side and the x-axis. So 7 pi over 6 is in quadrant 3. So if I draw a picture of that, it's going somewhere down here. Now I want to figure out my reference angle is just the angle between the x-axis and the terminal side, so that little part. So our 7 pi over 6 is, it has an extra pi, and then there's the little reference angle. So if I take 7 pi over 6 and I subtract off pi, I do need a common denominator. So I'm going to sneak in a 6 over 6 there. So 7 pi over 6 minus 6 pi over 6 is a pi over 6. So that is our reference angle. Now pi over 6 on the unit circle, that's 30 degrees, has the ordered pair. Square root of 3 over 2 first, and then 1/2 second. So that's our ordered pair for pi over 6. So for 7 pi over 6, we're going to have the same numbers, the square root of 3 over 2 and the 1/2, but because we're in quadrant 3, we're going to make both of those negative. So that is the coordinates for 7 pi over 6. That's one of the ways to think through that. Now, you're not going to have to do this particular thing on the exam. And in the future, you'll actually have the unit circle, so you'll have this information like readily available. But remember, when we look at these coordinate pairs, the cosine of this angle, 7 pi over 6, is going to evaluate to be negative square root of 3 over 2. And the sine of that angle is going to be negative 1/2. So let me sneak that in above. Like when we say this is the ordered pair, this is part of the information that we're saying. So we've spent a whole lot of time focusing on the sine and the cosine.
Could the radians ever be negative? Like if I was like 5 negative?
Okay. It's the same thing it means if the degrees are negative. So instead of measuring counterclockwise, they measured clockwise. And just like you could add 360 and get a coterminal angle, you could add 2 pi to get a coterminal radian angle. So that way you could look at the positive number instead of the negative number. All right, so here we've got a big giant summary of almost everything that's on the unit circle. There's our 3 special right triangles, all those ordered pairs. The only thing it's missing is the ordered pairs for 1, 0, 0, 1, -1, 0, and 0, -1. But otherwise, all of that is what you should have on the unit circle. And I did post an announcement that has a worksheet where you can practice filling in quadrant 1. It's an exact copy of the same diagram that we have on exam 1. All right. So let's see here. So same diagram, we don't have all the angles written in here, but notice the bow tie shapes. So we have these 4 red points that make a more normal, like long skinny kind of bow tie. All of those red points have a 30-degree reference angle and have the same coordinates. The only thing that's changing is the negative sign. So all 4 of them rather, have square root of 3 over 2 as the x coordinate. It's just 2 of them are negative, 2 of them are positive. All 4 of them have 1/2 as the y coordinate. 2 of them are positive, 2 of them are negative. The same thing for our blue bow tie. That's our 45 reference angle triangles. And then our green bow tie, the really tall but kind of skinny one, has 1/2 the short x coordinate and square root of 3 over 2 the tall y coordinate for all 4 of those points. So the unit circle has a lot of patterns to it. And as you fill in that chart, if you haven't done it already, like this is another nice pattern to look at. Because if you know quadrant 1 and you know about this pattern, you know the other 4 quadrants, the other 3 quadrants. Now there's a song you can play on your own time that can help with that. Okay, so this particular slide, we don't really need this information until we start looking at the graphs after this next exam, but it doesn't hurt to think about it right now. So when I'm thinking about the domain, those are the inputs for sine or the inputs for cosine. So when I say the sine of something, what kind of thing is going inside sine? Like here, let me flip it back. Like here, I wrote the cosine of 7 pi over 6 and the sine of 7 pi over 6. So 7 pi over 6 here is an angle, right? So those angles, like we could put in any angle number we want because we found that all of these angles are coterminal with something between 0 and 360. So we're generally only going to focus on the 4 quadrants from 0 to 2 pi or 0 to 360. But technically, the domain for sine and cosine is any angle number. So it is all real numbers. We could put in any number into these 2 functions. Ugh. Okay, so we got negative infinity to infinity for our domains. Now our range is a little more interesting. So we saw this when we were looking at those quadrantal angles. So the sine starts at 0, it goes up to 1, then it goes back down to 0, it goes to -1, and then back to 0. And as we increase the angles past the 360, the sine is going to follow the same cycle of values. And I'm using the word cycle on purpose here because it is a cycle. It's going to repeat the same values over and over and over again. But the absolute smallest sine gets is -1. And the absolute biggest sine gets is +1. And then the same for cosine. Cosine runs through the same cycle. It just does it it starts at a different place than sine does, but it runs through all the same values. So this behavior makes these trig functions very interesting. They actually have a lot of interesting uses in calculus, particularly when we're looking at a lot of crazy limits. The fact that sine and cosine are bounded, like we can exploit that to figure things out about them. All right, now the matching activity here is asking us to match. We're going to be matching triplets. So I've got a bunch of degree numbers. I've got radian numbers. And I've got ordered pairs. So like 0 degrees here is the same as 0 radians. And the ordered pair point that goes with those angles is the point 0, 1. So those three go together as a 3 of a kind. So this is just practice associating the 3 of a kind. Nope. I can't do my math. The point on the right is 1, 0, not 0, 1. So our 90 degrees goes with 0, 1, and 90 degrees is pi over 2. So it actually displays up top when you've got them correct. So I'll leave you guys to play around with that. It's good practice associating everything. So the new material, this is the second half of section 2.3, is these extra 4 trig functions. So we have tangent, secant, cosecant, and cotangent. The book likes to define these things in terms of x and y. But again, those definitions are only true when we're on the unit circle. So I prefer to define them in terms of sine and cosine, which is what the blank over here is for. So secant here is listed as 1 over x. And remember, x was our horizontal side, that's our adjacent side, so it goes with cosine. So secant is the reciprocal of cosine. Then we have cosecant is the reciprocal of the y value, which is sine. Now tangent up here is defined to be y over x. Y is associated with sine. X is associated with cosine. So tangent is the same as the ratio of sine to cosine. It is also the ratio of opposite over adjacent. That's our tripping on acid from our acronym. And then cotangent is the reciprocal of tangent. So that means it's cosine divided by sine, which means we'd flip over our OA, it'd be AO. My cosecant's the reciprocal of sine. Sine is opposite over hypotenuse, so this one becomes hypotenuse over opposite. And then likewise, secant ends up being hypotenuse over adjacent. So we're going to have practice with this in a second, but I just want to kind of look at this and kind of look at some of the tricksy parts here. So sine, cosine, and tangent are our main 3 trig functions, the way trig is taught now. And then secant, cosecant, and cotangent are reciprocals of those main 3 trig functions. So when I look at secant, cosecant, and cotangent, cotangent has a t in it. Tangent has a t in it. So that's one of the ways I remember that cotangent is the reciprocal of tangent. So tan and cot, those guys are reciprocals. Then for our secant and cosecant, so when people write secant and cosecant and they're like, all right, which one's the reciprocal of which? This is where people will get kind of flustered. So it'd be really nice if secant was the reciprocal of sine and cosecant was the reciprocal of cosine, but they're not. So it's kind of backwards. There's a historical reason why we studied sine and secant as their own things. And then the cosine is the sine of the complementary angle. The cosecant is the secant of the complementary angle. So it just turned out that the cosecant was the reciprocal of sine, just based on the way the ratios were originally working. All right, so let's actually use these guys. So here we have an ordered pair. The angle is in quadrant 2. And we want to fill out the values for all of these. So the sine value, when I look at my ordered pair, is the sine the x or the y? The y. So our y is 1/2. So our value for sine at this particular angle is 1/2. And then our cosine is going to be the other guy, the negative square root of 3 divided by 2. Now we're going to figure out the other 4. So tangent is sine divided by cosine. So that is going to be 1/2 divided by negative square root of 3 over 2. So 1/2 divided by negative square root of 3 over 2. So that means we would multiply by the reciprocal. So we're going to get 1/2 times 2 over negative square root of 3. And we end up with 1 over negative square root of 3. Now, if I try to type this, it's like, I hate your answer. And if I'm like, oh, maybe I put the negative in the wrong spot, like, let me move that in front of the fraction. No, it still hates it. Why does it hate it? Because I put the square root on the bottom. So we got to multiply by the square root of 3 over the square root of 3 here. So we're going to end up with negative square root of 3 over 3. That's what they want us to type here. All right, now we've got the other 3 guys. We're going to figure out our reciprocals. Now our cotangent here is the reciprocal of tangent. Now remember, we had for tangent, though, that 1 over negative square root of 3. So cotangent, we can make use of that irrational fraction here. So we're going to get just the negative square root of 3. So we're going to scroll down, fill in that. All right. So now cosecant of t and secant of t. So we got to remember which one's which. So one of these is 1 over sine, one of these is 1 over cosine. Which one's which? So is secant 1 over sine? I see some yeses and some nos. So I put S with S. Does the S go with the S? No. So secant is 1 over cosine. And cosecant is 1 over sine. So sine was 1/2, so our cosecant is 1 over 1/2. So cosecant is a lovely 2. Secant is going to require a little more work, though. So this is 2 over negative square root of 3, but we got to rationalize it. So we end up with negative 2 times the square root of 3, and then that whole thing is divided by 3. So on the exam, you're going to have to, we're going to give you one of the trig values. We're going to give you sine or cosine, and we're going to tell you the quadrant it's in. From that, you're going to figure out the other of sine or cosine, and then you're going to figure out the other 4 trig functions. So you do have to remember the formulas that cosecant is 1 over sine, secant is 1 over cosine, cotangent's 1 over tangent, and that tangent is sine over cosine.
How did it negative 3 for the negative 3?
Negative square root of 3 over 3. So tangent was sine divided by cosine. Sine was 1/2. Cosine was negative square root of 3 over 2. So we had that as division, and then I changed it to multiplying by the reciprocal. So we had 1/2 times 2 over negative square root of 3. And then the 2's cancel, so we have this 1 over the negative square root of 3. But that answer is, it's considered an improper fraction. So we multiply it by the square root of 3 over the square root of 3 so that the square root isn't in the denominator. So on top, 1 times the square root of 3 is square root of 3. And then on the bottom, square root of 3 times square root of 3 would be square root of 9, which is 3. And then it was negative, so I just moved the negative to the top. So that's how that negative root 3 over 3 kind of came out of nowhere. But when we did the cotangent, I used the form we had before, the 1 over negative square root of 3, and we flipped that to get just negative square root of 3. So we didn't have to do another rationalizing step. Now, the good news is on the test, there won't be square roots here. It'll just be numbers. So when you flip the fraction, you're done. You don't have to rationalize. Web work will have some ones where you have to rationalize. So it is in the web work homework. And it is also in the practice problems for the exam. So those practice problems should be open in web work now. And those practice problems are going to be worth 10 bonus points on your exam score. So even if you get 100, that'll bring your exam score up to 110. One over 1/2 in parentheses. Yeah, fair. My writing is cramped. All right. So what other questions do you guys have on this one? I squeezed a lot of information on there, so any of the questions about my handwriting are totally fair here. So I know this can feel like overwhelming because it's a whole lot of stuff right at once. But with practice, this does become a lot more familiar. So let's take a look at another one. Well, so what we have here is we have the cosine and the sine values in a table, and then across the top we have the angle measures from the unit circle in radians and degrees. And then underneath that, they filled in the tangent, secant, cosecant, and cotangent values. Now, sure, technically you could memorize this table, but like nobody I know does. If I need to figure out what the values are for any of the other four functions, I go back to their definitions, remember what sine and cosine are for that angle, and then figure it out. But I do want you to notice, because all the other ones are involving sine, like either sine or cosine in the denominator, and sine and cosine can take a value of 0. The other four trig functions have spots where they're undefined. And when we look at those graphs after exam 1, those undefined spots are actually going to be asymptotes. So that's where the behavior in those graphs gets interesting, or at least weird. But overall, this is just a summary table. You do not have to memorize it. It's just presenting the information in a slightly different way so you can see some of the patterns. All right, so here we're going to make use of some reference angles. So they've given us an angle of -5 pi over 6. So that is, first we want to figure out where the heck that is. Our picture over here on the left is listing where each of the trig functions are positive. So in quadrant 1, everybody is positive. So I generally call this one all. Then in quadrant 2, sine and its reciprocal are positive. In quadrant 3, tangent and its reciprocal are positive. And in quadrant 4, cosine and its reciprocal are positive. So sometimes this is remembered using the acronym all students take calculus. Moving in the quadrant order. So if you watch my videos, like I'll sometimes write this ASTC diagram in the notes, and that's just referencing where is the thing positive, or which quadrant are we in, what do we know is positive here, what do we know is negative here. This is just a summary mnemonic device to help you remember that. Now, when we're looking at that -5 pi over 6, so that is not quite negative pi. So negative pi would measure all the way to the line. So -5 pi over 6 is somewhere in quadrant 3. Now, the nice thing about our radian degrees, our radian measures, is the reference angle is what you see. So that denominator is 6. So our reference angle is pi over 6. But we're going to run through the calculation sum. But before we do that, I need to clear the screen. Otherwise, my doodles are going to get in the way. So does anyone still writing what I wrote up there? So we clear that out. All right, so negative 5 pi over 6. If I add 2 pi to that, and I multiply the 2 pi by 6 over 6, I have 12 pi over 6, so negative 5 plus 12 is positive 7 pi over 6. And then if I subtract pi from that, I end up with pi over 6 as my reference angle. Now my ordered pair for pi over 6, that's 30 degrees, so it's closer to the x-axis. The x is longer. So square root of 3 over 2 and 1/2. So when we look back at our negative 5 pi over 6, which is coterminal with 7 pi over 6, those are in quadrant 3. So our ordered pair, we're going to keep the same signs, or the same numbers. So we'll have square root of 3 over 2 first and 1/2 second. But we're going to make those x and y coordinates negative. So our reference angle in here, though, is pi over 6. And now it gives us the table to check our numbers again. So the sine value, negative 1/2. Cosine is negative square root 3 over 2. So the values we're going to get here are going to be the same values we got on the previous problem. We just have to pay attention to what the positives and negatives are. So I'm going to like speed the calculation a little bit. So tangent is sine over cosine. Our sine is negative 1/2. Our cosine is negative square root of 3 over 2. So we have tentatively positive 1 over the square root of 3. And then we saw when we rationalized that, it became square root of 3 over 3. Now we just got to play around with the other guys. So I will kind of habitually, like once I've done tangent, I like automatically go to cotangent because I just want to get it out of the way. That's the one I know it goes with tangent. I just figured out tangent, so I may as well do cotangent right away. So 1 over tangent is going to be 1 over that 1 over the square root of 3. So we get positive square root of 3 for cotangent. Now we just got to remember the difference between cosecant and secant. So secant is 1 over what? Which one?
Fine.
So secant and sine?
Oh, no, it's the beginning, cosine.
Yep, secant and cosine. So when you're writing this step, like it's helpful to even say it out loud, like cosecant is 1 over sine. Secant is 1 over cosine. S and C, C and S. And now we'll actually finish out the calculation. So sine was the negative 1/2. So 1 over negative 1/2 becomes negative 2. Then our cosecant is a little more annoying. 1 over negative square root of 3 over 2. So we have negative 2 over the square root of 3, which we end up with the square root of 3 on top and just a 3 on the bottom, still with that negative 2. So negative 2 square root 3 divided by 3. Yeah, this table has a typo. Finding the coterminal angle?
Yeah.
So negative 5 pi over 6, it's negative, so it's kind of weird to think about. So I added 2 pi to it just to see a more normal looking angle. But to add 2 pi, we need a common denominator. So that's why I multiplied the 2 pi by 6 over 6. So on top, that's really 12 pi over 6. So negative 5 plus 12 is positive 7. So that's how we got the 7 pi over 6. 7 pi over 6 is a little bit bigger than pi, so we know that's in quadrant 3. So that's why I have like that note down below. But then I subtracted off pi because I wanted to know what the reference angle was. The reference angle is the distance from the x-axis to the angle. So in quadrant 3, sure, something like that. So down here in quadrant 3, I can see that I've got my full arc for pi, and then there's a little bit more to get to a quadrant 3 angle. So that's why I took my full quadrant 3 angle and I subtracted off pi, because that's that 180 degrees, and that'll leave me with my leftover reference angle. So that's why I have the minus pi here. And then I just multiplied by 6 over 6 for the common denominator. So that left us with pi over 6 is the reference angle, which is 30 degrees. So I pulled from my own memory that 30 degrees has this ordered pair, and then we used that to figure out what the ordered pair had to be for 7 pi over 6, which is coterminal with the negative 5 pi over 6 that they gave us. So you could technically figure out the reference angle just from the negative 5 pi over 6. The calculation is a little bit weirder. All right, now the negative 2 square root of 3 over 3 is correct, but the table got misprogrammed and it thinks it's positive. The negative is actually correct, though. So what other questions do y'all have on the way this shook out? Because these can get like kind of intense. There's a lot going on there, especially with the weird square roots and having to rationalize. All right, let me see what the rest of this has. So even versus odd. And Pythagorean identity. All right, so some of these slides I go on purpose. So this right here is a set of like very optional extra facts that are true about the trig functions. So some of the trig functions meet the definition of an even function. Some of them meet the definition of an odd function. Back when we used to graph everything by hand, knowing this like let you take shortcuts in your graphing. So like knowing a parabola is even, if you graph the right side of the parabola, you can mirror image and get the left side of the parabola. Or if you know something is odd, when you have one side of the function, you do a like rotational 180 degrees and you can get the other half, which is what's going on with x cubed. Or it's a like reflect over and reflect down. So the trig functions also have these properties and they've got little proofs there for it. Mostly though, we can see it on the unit circle itself. The cosine of a positive angle versus the cosine of a negative angle, the cosine of those is the same because they're both positive x. If I look at the sine values though, the sine of positive t is y. The sine of negative t is negative y. So it turns out the sine function has this weird opposite operation. So I would have to add an extra negative, so it's sine of t equals negative sine of negative t. Like that's usually the way it ends up being written. I think I deleted this question from the homework, but if it's still in there, like basically anytime you're seeing trig function of negative x, it's either the same value or the opposite signed value. So this is just like a bonus property, but we don't really make a lot of use out of it. I don't think it even really shows up that much in Cal 1 or Cal 2. It technically could, depending on how a professor talks about stuff, but meh. So basically, all of this is just saying there are certain weird symmetries in the trig functions. They do follow one of these two rules. Most of the functions we study don't fall in either category. So this isn't a everything is one or the other. Most stuff is neither even nor odd. Like if we think it almost every other quadratic, most quadratics, like once I move it over, I can't fold it along the x-axis because I have to fold it on the line that goes through the parabola. So the parabola has symmetries, but it doesn't meet this definition of even for most parabolas. It's just the special cases where the vertex is on the y-axis that it happens to be even still. And the same with the odd functions. Like once I shift it around a little, it doesn't meet the definition of odd anymore. But we really don't use this that often. Now this one though, this is a little basic introduction to some of the identities. So we've talked about the reciprocal identities. We were just using those to do our, figure out the rest of our functions. And the fact that tangent is sine over cosine. The cotangent being cosine over sine is just coming out of the fact that the cotangent is the reciprocal of tangent and tangent is sine over cosine. If I combined those two identities, I'd get this secondary quotient identity. Down here, our Pythagorean identity, sine squared plus cosine squared equals 1. That is coming from our formula for the unit circle. X squared plus y squared equals 1. Like technically then I'd write cosine squared plus sine squared equals 1. But with addition, we can swap the order. So typically when we write the identity, because we usually say sine before cosine, we typically write it sine squared plus cosine squared equals 1. Now, if I take what it's asking us to do in the blank is prove one of those other two identities. Now, you are going to have to do this on a writing assignment, but it's like module 7 writing assignment, I want to say. But it doesn't hurt us to look at it here because it's going to reinforce all these other identities. So if I take a look at my sine squared theta plus cosine squared theta equals 1. And what I want to do is make steps using the formulas I already know to arrive at one of these other formulas. So down here, I'm going to write tangent squared theta plus 1 equals secant squared theta. So on first look, it's like, I don't know what's going on there. Like, everything changed, shit moved around. That's not a perfect move because if I tried to move the one, I'd minus it, and this is a +1, so I'm not moving the one. What do I know about secant though? What do I know secant is the same as? What does it say secant is the same as over there? 1 over cosine. So I'm going to trade that out here. I can't do much trading with 1, but tangent squared. I know tangent is sine over cosine. Now start looking at the structure of our first line and the structure we have down here. So it's kind of weird with the parentheses. So I'm going to bring those parentheses inside, or bring the squares, like sine over cosine whole thing squared is the same as sine squared theta divided by cosine squared theta. And then over here, 1 over cosine whole thing squared is the same as 1 over cosine squared theta. So now let's pattern match a little closer. So I started with sine squared, and then I do some stuff, and then I have sine squared over cosine squared. On the right, I started with 1, some stuff happens, and I end up with 1 over cosine squared. So what stuff does it look like is happening? Like, is there something I can do to my first equation so it looks like this middle step I have here? Like, what does it look like they did?
Would the sine squared theta over cosine squared theta just be 1?
Well, sine and cosine are not the same.
Oh, I see. It would be,
Like, sine over cosine is tangent. But if I had like cosine over cosine, that would be 1. So cosine squared over cosine squared could be 1. So you see how on top of sine squared over cosine squared, like I have sine squared on top, and my first line had a sine squared. On the right side, I had a 1 on top, and my 1 was what I had on the right. But the new thing is they're being divided by cosine squared.
with the 1 substituted. Sine squared.
So you're saying in place of the 1, write sine squared theta over sine squared theta?
Place of the 1 over cosine squared theta, the 1 instead would be sine squared theta plus cosine squared theta.
We could do that. That is going to introduce, that would be if we wanted to make the left side look like the right side. We would do that. Here, the structure is a little bit different. We're trying to make the top line look like the bottom line. So it's a little bit different from identity work you may have done in previous pre-cal courses. What if I put this here? Cosine squared over cosine squared is the same thing as 1, right? So now you see everything on top of these fractions here in this middle line is our original equation. And then everything on the bottom is the same, right? So could I take my original equation and do the same thing to both sides, does that keep the equation true? As long as it's the same thing, I can do that. What same thing, what operation could I do to both sides here so I produce this equation down here? Like, what did they do to the 1 to turn it into 1 over cosine squared theta? And it's kind of a silly question because the question, like the answer is almost the question itself. They put 1 over cosine squared theta. So I apologize for the awkward questions. Like I know sometimes it's really hard as a teacher to find the right question to get the answer you want without giving away the answer in the question. And so sometimes my questions fall short. I don't want you guys to get frustrated with yourself if you're like, God, I didn't know what the heck she was asking. Like, that's on me for not finding the right question. Like, sometimes I'm trying to ask a question and it's just, there isn't a good way to phrase the question. But the idea here is, if I start with my sine squared plus cosine squared equals 1, and I choose to divide both sides by cosine squared, I can split the fraction on the left, like kind of pull out the squares, and then use my reciprocal identity and quotient identities to make a substitution and end up at this other Pythagorean identity. So we're going to see this whole process again, but did the steps we did kind of backwards working at the bottom make sense? Like the seeing the whole divide by the cosine squared is definitely the weird thing that's out of left field. But everything underneath that, like how we moved backwards through those steps, does that make sense? Like making those substitutions for tangent and secant, and then seeing squared could kind of be distributed, and that 1 is technically the same as the cosine squared over cosine squared. That part's a little weird. But basically, like the only thing we really want to focus on right now is just getting used to these identities and being able to make those substitutions. So now this one is like almost exactly what's going to be on the test. So they're telling us that the cosine of t is 12/13. So 12 over 13, boom. And you know what else? Which one of these guys down here is the reciprocal of cosine? Yep. Secant is the reciprocal of cosine, so I may as well grab the low-hanging fruit. So that is 1 over 12/13. So that becomes 13/12. All right, so I've got 2 out of the 6. And they happen to tell me t is in quadrant 4. Now I know that extra information is just going to help me figure out if I want positive or negative. So let's focus in on what else I can figure out. I know cosine. I want to figure out what sine is. I know sine squared plus cosine squared. Like technically I should be saying sine squared of t plus cosine squared of t equals 1, but saying the of t gets a little tedious, so sometimes we'll drop saying it, but technically you should still be writing it. So they told me cosine is the same as 12/13. So I'm going to make that substitution. I'm going to put 12/13 in place of the cosine. But that cosine is still being squared. I still have sine squared of t. And this is all equal to 1. So I'm going to finish solving this so I can get sine squared of t. So 12 over 13 squared. That's 144 over 169. It is absolutely totally normal to type that on the calculator and crunch it up. I don't expect you guys to do this by hand. I just happen to be a math teacher who does way too much mental math, so I happen to know these numbers. But that is absolutely not my expectation for y'all. Now my next step, I got that 144 over 169. I want to get sine squared t by itself. So I'm going to subtract that fraction to the other side. And this is absolutely when I would recommend using the calculator. Even if you happen to remember your squares, doing this math is like, eh. That's definitely the point where I usually make mistakes. So that's usually where I'll resort to the calculator. So can someone crunch up what 1 whole minus this fraction is? I know it'll be over 169.
What?
Yep. So sine squared of t is the same as 25 over 169. All right, now how do we get sine t by itself? Yep. And then what else do we have to remember with our square root? Yep, so we have to decide, do we want the positive or the negative here? So they told us t is in quadrant 4. And in quadrant 4, cosine is positive, which we know they gave us a positive number, so sine is negative. So we're going to choose the negative square root. So sine of t is negative. Now here, you can just crunch the square root on your calculator, but square root of 25 is 5, and 169 we got earlier from squaring the 13, so it better go back to a 13. So it turns out the sine here is negative 5 over 13. So now I've got 3 of the 3. And in fact, I can sneak ahead and fill in the cosine. That's just my reciprocal of sine, so negative 13 over 5. So now I just got to figure out tangent so I can then do cotangent. So let's see if we can't squeeze that in here. Tangent is sine over cosine, so it'll be negative 5/13 over 12/13. And then the 13ths cancel, so it's just negative 5/12. And then that means our cotangent will be the reciprocal of that, negative 12/5. So this particular question is actually like you show a fair amount of work going from the cosine to the sine. Like there, I expect to see some work. But once you've got that work done and you've arrived at, here's what my sine value is, now you have sine and cosine, you should be able to get the rest of those. So you may do a little work for the tangent, like showing sine over cosine, simplifying the fractions out, or just like having this, and then you're like, boom, here's what my calculator told me this was. The reciprocals, you may not actually show a lot of work, and I'm okay with that as long as I'm seeing that you wrote the reciprocal of cosine for secant, you wrote the reciprocal of sine for cosecant, and you wrote the reciprocal of tangent for cotangent. But if you're afraid of messing stuff up, like go ahead and do the extra step and just write down like cosecant is 1 over sine. That way, if you mess up the numbers and write the wrong thing, you've still shown me that you remembered that thing was 1 over sine correctly. So on the exam, if you're getting the right answer, you don't have to show me work. So if you've done these enough, you're like, I know it, I get it, I'm good. Cool. If you're not as sure on it, like show me a little extra work so that way I can give you partial credit. That's the big thing on the test. Like the more work you show me, the better a chance I have of giving you more partial credit. But if all you show me is just an answer and it's coming out of nowhere because there's no work, then I'm like, I don't know. In fact, for some problems, if you don't show me work and you just produce an answer, I'm not going to give you all the credit because on some of the questions, I need to see your thought process. I need to see those steps worked out. So on this one, I'm telling you like how much work you can get away with skipping You can skip some of the work on the reciprocals, most of the work there, but I do want to see the work for getting from your cosine value to your sine value. Now, it doesn't have to be all the steps I have here. Like if your brain works faster than that, if you're comfortable like crunching quite a bit on the calculator, that's okay. But like I generally try to say like, show me at least like a substitution step, some in between step, and then your answer. Like show me some work. Or if you somehow manage to do everything on the calculator and you have time, like try to explain how you did it on the calculator. Like I know some people who just, the way their brain works, like they can just like zip zoom and do it all on the calculator and like boom, answer. And if I watch them do it, then I'm like, yes, you know what you're doing, we're good. But most of the time, if I just see an answer appear out of nowhere, I'm like, it looks like you just copied the answer. Which I don't want to assume that, but if there's no work. And also we have more than one version of the test, so I don't recommend copying because they're not going to have the same numbers and it looks really fishy. All right, so with a little more practice, does this problem feel like it's doable for the test? And that's one of the full questions is doing this whole process. So it's 8 points for giving me like the sine value, and then like 3 points each for the other 4 functions. So 12 points for those, for a total of 20 points out of the full 100 on the test. So this one people usually do pretty well on the values. The mistake people tend to make is whether it's supposed to be positive or negative. So if you make a mistake like on the sign and you don't determine the correct, whether that's positive or negative, but then your other 4 things are correct, if I assume your sign value is correct, I'll give you the full credit on the other 4 and I'll only take off points on doing the sign value wrong. Like, does that make sense? So if you make the mistake in one spot, I'm not going to continue to take off points in the rest. In most problems, there's a few problems where if you make a mistake early on, it just kind of screws you from being able to do the rest of the problem. And then I can't see that you could do the problem. On this one, though, the mistake is not so derailing. All right, so this next slide is just another coincidental fact. But our trig functions, because they're based off of a circle and a circular is repetitive, the values repeat on these functions. So they are what we call periodic because they have a period of values and then it repeats again. So a period is something that occurs regularly on a cycle. So the period for sine and cosine is 2 pi. So cosecant and secant also have the same period of 2 pi. Tangent and cotangent, just based on the way the numbers work on the unit circle, they actually repeat more frequently, and they run through all of their values from 0 to pi. So they do technically also run through all their values from 0 to 2 pi, they just run through them twice. So they are all technically periodic on 2 pi, it's just the tangent and cotangent happen to be faster. We're really going to focus on this when we get to the graphs though, so this is just more like preview information for when we do graphs later. Now, if you want here, there is a link to an online unit circle quiz. You don't have to, but you can like take it and then post your accuracy and maybe see some other people, see how you rank. And then we have such a cheesy attempt at a pickup line. Hey girl, what's your sign? It must be pi over 2 because you are the one. And only Sheldon would think, that's actually brilliant. But we still have time. Has anyone started looking at the web work? Are there any questions on the web work that you guys would like to see?
I was having trouble with the direct conversion. It was on, I think, 2-2, or no, 2-1, sorry.
Nope, 2-1.
I believe it was this, like,
So yeah, somebody online was also saying 2.1 question 2. And then the other question, so on your work, you don't have to justify each of your steps. So you don't have to like write a sentence when you do a step. Like the first writing assignment was kind of weird because the very first question you actually had to write a sentence. That's weird. Most of the time you're just going to be writing math and you don't have to justify it for each step. But I do get people who ask that question because some professors like will ask for that, but I don't. Just as long as your work is making sense, you're fine. So one like this,
Yeah, that's the one I was having problems with.
all right, so let me yoink a picture of this and then come over here to web work and paste it, but then I have to flip the share to OneNote rather. Here we go. All right, so when we're doing our conversion, they're giving us degrees to start with. So I'm going to pick negative 265 because it's the ugliest looking to me. Now, what I want to do is when I'm doing my conversion, I'm thinking about this like units, just like I would in chemistry, or when I'm doing like inches to feet or hours to seconds. So right now I started with degrees. So that's a unit on top. So I want to write that unit on the bottom so the degrees would cancel. And then this is asking me to move 2 radians. So I'm going to write radians on top. So now that I have where the units go in the fraction, now I can fill in the numbers that I know go with those units. So just like we'd fill in like 60 minutes in an hour versus 1 minute is 60 seconds, like where those numbers go depends on the units. So what do we know about radians and degrees?
There's 2 radian or 1 radian for 180.
Pi radians for 180. So 1 radian is a weird 57.3. It's somewhere in quadrant 1 because the 1 radius, and then 1 arc, it'd have to be in quadrant 1 because 1 isn't that big. So that's why it's 2, 3, and a little bit extra. 3.14 is what makes us all the way to 180. Just another way to maybe make those two stick. Now that we've got those units set up, my degrees cancel, and I just have to crunch the numbers. Now, depending on your calculator, you might be able to type all of this and it'll spit out the answer with the pi. Some calculators, though, if you put the pi in there, then it's like, I hate you, all I will give you is a decimal. In which case you can crunch the numbers just themselves. And then depending on the calculator, there's like a button that's like fraction to decimal. And it may not be a button, it may be a shift button, but this would tell us what the reduced form is. And I can calculate that, but it'll take me longer because my phone calculator don't do that nicely. So I know those are both divisible by 5, so 53. And then 180 divided by 5. So it looks like 53 over 36. So this is negative 53 pi over 36. So this is like what we did on the calculator, and then how we translate that into the answer.
Thank you. I don't about that button actually.
Yeah, it's,
Oh, that's all. Like, okay.
yeah. Now, some of the calculators, if you type it in with the pi, it'll spit out negative 53 over 36, and then it writes the pi next to the fraction. Just type it with the pi on top of the fraction. And WebWorks should take it either way, but sometimes it can be weird.
Question about the I don't know if they're like tutoring people right next door. What room was it again? It was like
Next door to where?
the guy came in who was like,
Yes. So the math gym is over in the Flan Sciences building. If you go up to the 3rd floor, it's room 30208. So when you come out of the elevator, you go left and then there's a hallway on the right. And it's like basically the third kind of door on the left. The second door in that hallway is my office. I share the office with like 10 other people, so it's a big room with a whole bunch of cubicles. But the next room is a room with a whole bunch of computer tables, and that's where the math gym is.
And do they like take in walk-ins or do you have?
Yep.
Okay.
So you can walk in at any time and anybody in the lab can help you with pre-cal. Because that's like our lowest level course. So the math gym is like pre-cal and up. Any math class past that, if we have tutors for it, that is where they are. There are other tutoring resources on campus, like the Tomas Rivera Center does math like up through college algebra, but they also do like English support, writing support. They've got a whole lot of stuff. I think there's also a writing lab run by the English department. I think like over there. Actually, I'm not really sure where the writing lab is, but I think there's another resource for that as
You
well.
mean the writing center?
Yeah.
Oh, I think that's in the library.
Oh, okay.
It's like South Commons or something.
So yeah, if you ever need somebody to like proofread your essays, there are resources for that. If you need someone to proofread your math, that's what the math gym is for.
Thank you.
Would you prefer the math gym or the Rivera Center? Like,
So for pre-cal and up, the math gym is better. Like we basically, we kind of steal the tutors from the TRC once they get advanced enough in math. Like, I mean, kind of fairly steal, like it's, you know, I don't know if we offer better pay, but
Thank you.
Have a great day.
y'all too? All right, let me